All right, it is 2, so we'll get started. And I think today should be relatively short because we just have a few example problems to go over, and then we're done with all the lecture for this class. So just some reminders about dates. Tests for this Friday. Hopefully you know the drill by now. 12 a.m. 11:59 p.m. You have to take it. Final exam. That'll be next week, Thursday through Friday. Opens at 12 a.m. on Thursday. Closes at 11:59 p.m. on Friday. Feel free to take it anytime you want. 2.5 hours cumulative. The only new information on the final exam that you haven't been tested on by the time you take it is the slideshow we went over on Monday and just what we're going to finish off today. All right, so the only thing we have left to do is just some example problems for inhibitors. So let's take a look at this. And I just wanted to start on this slide again, as remember, this is the good slide to come back to try and remember how to do these inhibitors. So here I have a series of 3 questions. So we have an enzyme catalyzed reaction, and we have 5 nanomolar of a reversible inhibitor, not inhibition, but inhibitor. And when I add that inhibitor, Vmax drops to 80% of the value in absence of the inhibitor, while the Km is unchanged. So using that information, 1 or A, figure out what type of inhibitor or inhibition is going on. Then B, what proportion of this enzyme will be bound to inhibitor. And C, calculate the inhibition constant. Remember, the inhibition constant is called Ki here. So I'm going to give you a little bit of time to do this. The bottom there is probably cut off a little bit, so I'll just rewrite it. Okay, prime I, and these are 1s. All right, so yeah, see if you can figure out what's going on with these problems. And I will be back like I'll give you a couple minutes on A, then I'll give you like a minute on A, then a couple minutes on B, then a couple minutes on C. So see how far you can get with these. All right, so for A, there's only 3 choices, right? Competitive, uncompetitive, and mixed. So if Vmax is decreasing, remember the Vmax of an inhibitor, we call that Vmax apparent. So Vmax goes down. That means it can only be one of 2. It can only be uncompetitive, whoops, wrong one, uncompetitive or mixed. While the Km's unchanged. Well, uncompetitive, the Km has to decrease. With mix, it can increase, decrease, or not change. So the only type of inhibitor is this is mixed. So that's for A. So with that, try and see if you can figure out, okay, what percentage is bound then. And just a hint, there's no equation that says it down there. So you have to think outside the box to figure that out for B. All right, so for B, here's the trick here. So let's say we have 100 molecules. And the maximum velocity of those 100 molecules is 100 reactions per second. That's just a hint. Whenever you're trying to figure out like math stuff, units of 100 always make it easy, or units of 10. So 100 molecules, Vmax is 100 reactions per second. Well, when I have the inhibitor, I'm 80% of that value. So I'm only going 80 reactions per second. Therefore, how many molecules are unbound? Well, if one molecule does one reaction every second, therefore I must have 80 molecules unbound if I'm still doing 80 reactions per second, which means, so that's unbound. If I had 100 total molecules to begin with, then I add my inhibitor, and now I have 80 unbound molecules. That means I have 20 bound molecules. Therefore, what proportion of the enzyme molecules have bound inhibitor? That would be 20%, or every 1 out of 5 have an inhibitor bound. I guess another fast way to do this is if you have a Vmax as a percentage, just do 100% minus that percentage. And that answers the amount that are bound. That's another fast way to do that. So that takes care of A and B. Now, see if you can figure out C, where I want you to give me a value of Ki. And you should have all the equations there that you need. So I'll give you a couple minutes to see if you can puzzle this out. Then I'll be back with the answer. All right, so C is definitely tricky. So let's do this step by step. So one of the equations that we actually need that's kind of hidden on here is that Vmax apparent is equal to Vmax divided by this alpha prime. Remember we talked about on Monday this idea of alpha. And alpha is just basically how strong an inhibitor you have. The bigger the value of alpha, the better the inhibitor that molecule is. And there's two different forms of alpha. Alpha is for Km. Alpha prime is for Vmax. And it's actually on this table. And it's right here. Right, so this is telling you this is the Vmax, and this is Vmax if you're being inhibited, and it's kind of also right here, right? So no inhibition is just Vmax. In mix, it's Vmax divided by alpha prime, right? And for Km, that's alpha prime Km. So that's the first equation that we need to know, that our Vmax apparent equals Vmax divided by alpha prime. And we need alpha prime because we want to get to this equation down here, which I'll rewrite. We are trying to figure out K prime I, or Ki prime rather. Ki prime is the inhibitor constant, right? This is what we're trying to figure out for C. And to get that, we need two parts. We need alpha prime and we need concentration of inhibitor. Concentration of inhibitors given in the problem. So that's no issue. But we need to get alpha prime. And we have Vmax apparent and we have Vmax, right? Because we said Vmax apparent's 80% of our normal speed. So let's say Vmax is 100. Again, you can actually call this number whatever you want. You could call it 1. You could call it 22. But I'm just doing 100 because that math is easy then. If Vmax is 100, Vmax apparent is 80, right? 80% of my maximum. So I'm going to plug that in. 80 for Vmax apparent equals 100 for Vmax divided by alpha prime. And I want alpha prime alone. So it's going to be alpha prime equals 100 divided by 80. Just multiply each side by alpha prime, divide each side by 80. That's how I got those switched around. And then when you do that, you'll find that alpha prime is 1.25. Once you have alpha prime, then you can go about solving for Ki prime, our inhibitor constant. So I'm going to do that on the bottom of the page. So 1.25 equals 1 plus inhibitor constant, or amount inhibitor, 5 nanomolars, divided by K prime I, or Ki prime. Subtract 1 from each side. 0.25 equals 5 divided by Ki prime. And I'm going to do the same trick over here to get Ki prime alone. Ki prime equals 5 divided by 0.25. And doing that, you get Ki prime equals 20 nanomolar. And that is how you figure out C. Like I said, C is super tricky because even though the question's rather simple, you have to do a lot of steps and a lot of lot of logical thinking and outside the box thinking, a lot of those critical thinking skills to work your way to that point. So yeah, like C is probably like the hardest type of math question I would ever ask in this class. But hopefully once you start like understanding, what does this alpha mean? What does Km? What does Vmax mean? And now that you've seen me work out a problem, hopefully you can make a little more sense. Right, so that's the big math portion for inhibition constants. What I want to go to now is Lineweaver Burke, right? So let's see if we can understand our inhibitions using Lineweaver Burke. Remember, Lineweaver Burke is our double reciprocal. So on the y-axis, we have 1 over velocity. On the x-axis, it's 1 over substrate. The y-intercept is 1 over Vmax. The x-intercept is negative 1 over Km. All right. So this problem is a little complex, so let me explain it to you. So line A, this blue line, is my enzyme and substrate with no inhibitor. And I have a bunch of other different lines, F, E, D, B, and C. I want to know which one of these lines, when you compare to A, shows you a competitive inhibitor. So A and blank show competitive inhibition. Which one shows non-competitive inhibition? Which one shows uncompetitive inhibition? Again, this is a way to reinforce what do these inhibitions do to Km and Vmax. So feel free to use the previous page for that table to refresh yourself on how that goes. Otherwise, let me give you like 2 or 3 minutes to try and figure this one out. All right, so let's remind ourselves how these inhibitors change our variables. So competitive inhibitor, Km increases, Vmax is unchanged. And again, the reason for that is if you're competing at the same spot, your substrate can outcompete your inhibitor. So your ultimate maximum speed of your enzyme never changes. But it takes more substrate to go half your speed, which is Km. So Vmax is unchanged. That means that the y-intercept is the same for competitive and the uninhibited enzyme. So the uninhibited enzyme is A, and there are two lines that intersect at the same y-intercept, line B and line E. All right. So we have to figure out which one would be showing competitive inhibition, E or B. So if Km is increasing, and remember this is a reciprocal plot, a double reciprocal, that means it's opposite. If Km increases, that means the reciprocal is decreasing. So as Km goes up, where it crosses on the x-axis should get closer to 0. So the only line that crosses at the y-intercept and has a bigger Km would be line E. So E is our competitive inhibitor for line A. Now let's go to uncompetitive. Actually, I have non-competitive, have those mixed up in my notes. So non-competitive is Vmax decreases, Km can do anything. Right, so if Km decreases, that means it goes up, right? So there's only two lines that go up, F and D. So we have to figure out, okay, which one would that be? Sorry, yeah, Vmax decreases, and so the line would be above it. So we have to figure out which one will it be, F or D. So to really answer this, we have to actually think about what uncompetitive means, because the answer is actually one of these two lines. So uncompetitive is that both Vmax goes down and Km goes down. And that means you have a parallel line. While non-competitive means you do cross, the lines will cross somewhere on this graph. So with that in mind, if we look at F, F is crossing line A, while D is not. So non-competitive would be F, while uncompetitive would be D. So just to reiterate, what you're looking for on the Lineweaver Burke when you're looking for competitive, non-competitive, and uncompetitive, competitive crosses y-intercept, same point. And x-intercept closer to 0. Non-competitive cross not, how to put this, cross somewhere. We don't know where the lines will cross. And when I'm talking about like crossing, I mean like uncompetitive compared to, or sorry, non-inhibited or uninhibited compared to inhibited. So those lines are going to cross somewhere. We just don't know where. But Vmax will decrease which means 1 over V max will increase because we're looking at reciprocal. So that's non-competitive. And uncompetitive, you're looking just for a parallel line. And the line has to be above the uninhibited line. Oops. Because V max is decreasing again, which means 1 over V max is increasing. So the line has to be above our uninhibited line. Right. So the previous problem, we looked at the math of Lineweaver Burke or of inhibition. Here we've looked at the Lineweaver Burke of inhibition. In problem 4, I think what we're going to do for problem 4 is this is what I wanted to do on problem 4 is to have you make your own Lineweaver Burke plot and figure it out from there. But I think we're going to skip that. It's a fun exercise, but it's really only fun when I can see you making your graph and walking around and do technology. And that the majority of you are watching this on YouTube. We're just going to skip that. But yeah, that ends Biochemistry 1 lecture. Any questions about anything at all? And if not, I hope you enjoyed this class somewhat, learned something from this class. I know the way to teach this class online like this is not ideal, but I appreciate you bearing through it, studying hard. Taking a class this level online is not easy. It takes a lot of self-discipline. So congratulations on sticking through it. Only a couple more things to do and you're home free. So just remember, test 4, Friday, final exam next week, Thursday and Friday. What I'll probably do is I'll probably do some kind of like sign up or some kind of poll later this week to see if there's a time when people would want to meet next week for an online final exam review. So I'll try to get that out. But yeah, if you have any questions about anything, even outside of what we talked about in class, like anything biochemistry related, never hesitate to email me. Even when you're gone and graduating, you still have a question, let me know. Yeah, I think that's all I really wanted to say. Again, thank you very much. Hope you enjoyed this class. And good luck on test 4 and the finals. Oh, what I was thinking there. Yeah, if you want like extra like tutoring sessions before that, whatever, I am available like pretty much 24 hours a day now. So do not hesitate to reach out for me. Otherwise, that's all I have for you. And yeah, so this will be the last time we meet at this 2 o'clock time frame. So good luck, study hard, and maybe I will see you next week. Take care.